Let's get going. First of all, let's look at the easiest way, I'll call it method 1, of adding fractions with different denominators. The easiest way is if you notice that if I just multiply the two denominators together to get 50, then if I multiply the 2/5 numerator and denominator by 10, which is the denominator of the other fraction, then the 1/10 by 5, the denominator of the first fraction, I've changed them both to 50ths. This gives me a common denominator, 25 50ths. Then, of course, I can reduce this fraction, if I want to, back to lowest terms, which is useful, particularly if you're working math here, because we're going to ask that you do that. Any fraction you wind up with needs to be expressed when you're finished in lowest terms. I see there's a common factor of 25 in the numerator and denominator. When I divide that out, I'm left with 1/2. This is the most straightforward way of working, but it gives you a common denominator. But there might be something you can do to get a common denominator which is less than what we get here, so that when you have to do the addition or subtraction, things work out a little bit more simply. Here's the other method. What we want to do is see if we can find some multiple of 5 and 10 that's the same. We would have an agreement then. If we look at this, let's start with 10. Notice I'm multiplying 10 by 1, 10 by 2, 10 by 3, 10 by 4 here. I'm going to do the same thing with 5. 5 times 1, 5 times 2, 5 times 3, and so forth. I notice here, as you can probably see just from observation, that if I can change the 2/5 to tenths, I already have tenths in the second fraction. Then I will have a common denominator, and in fact it's called the lowest common denominator and sometimes the least common denominator, but LCD is what you see as the acronym or the abbreviation of lowest common denominator, least common denominator. It's the smallest number you can divide those two fractions up into so that they have the same denominator. How do I get 2/5 into tenths? I need to multiply by a 2, and of course to change 10 to tenths, I multiply by 1. If I do something to a denominator to keep the value of the fraction the same, I need to do it to the numerator. I can then have 4/10 as 2/5 plus 1/10. Now I can do the math. 4 plus 1 is 5, as we saw how to do in Unit A. You just add the numerators and put the sum over the denominator. What I did here was found the lowest common denominator or least common denominator, depending on what you want to say. We can see how this works by looking at the squares. There is 2/5, and by cutting the 2/5 in half, I make 4/10. Then I have 1/10. 4 plus 1 is 5/10. This is just as I did with the pies at the end of Unit A, cutting them up so that the slices are all the same size. Let's do this again for a slightly more interesting problem. Let me add a quarter to 3/14. I need to find a denominator that's common to these. One way to do this, to find the least common denominator, is to start looking at factors of 4. 4 times 1, 4 times 2, 4 times 3, 4 times 4, and then do the same thing with increasing factors of 14, and look to see where I have the same number. I see that 4 times 7 is 28, and 14 times 2 is 28. I can change the 1/4 to 28ths, and I can change the 14, the 3/14, to some number of 28ths by multiplying by the appropriate factors, because I see that that's a number common to both of those denominators if I keep multiplying. Let's change them. What do I need to change 1/4 to 20/8? I need to multiply by 7. What do I need to change 14 to 20/8? I need to multiply by 2. What you do to the denominator, you need to do to the numerator. Now I have 7/28 plus 6/28. I found a lowest common denominator. I can certainly find bigger denominators. For example, double 28, 56, could also be used as a denominator, but it wouldn't be the lowest common denominator. I can work this out. I get 13/28, and I ask myself, is that the lowest terms? Can I reduce this fraction anymore? There is no common factor between 13 and 28. It might occur to me maybe to try a 2 there. 13 times 2 is 26. Nope, not going to work. That's the answer. Let's look at the rules for doing this. First of all, with method 1, we can find a common denominator, not necessarily the least, but a common denominator. If we multiply the two denominators together, then we know we can change those two fractions to the denominator of one times the denominator of the other. It's not going to be the smallest number. Remember, when we did that with a fifth and a tenth, we got 50, whereas we could just as well have used a denominator of 10, a much lower number than 50 that we got multiplying the two together. Method 2, let's find the lowest common denominator by counting off and finding a common factor. What we do is we upscale the fractions to some equivalent fraction that have the same denominator. Then we add or subtract the numerators, just as we did in Unit A, and then we simplify. We take what we have. If it's an improper fraction, we turn it to a mixed number. If it is a fraction that can be reduced by dividing out common factors between numerator and denominator, we do that. Let's shift our attention now to rational expressions where we have unknowns as well as numbers. Numbers, you know, we can always combine together, but when we have variables as well, we have to be careful because we need to make sure that before we do anything in terms of adding or subtracting, we have like terms, or we just have to express it as two separate terms if we can't add them. For example, here we have 3 over 2y squared plus 5 over 3y. We see now we have two different denominators, and we need to find a common denominator, hopefully a least common denominator. You can always multiply the two together. Method 1. Let's investigate, though, method 2, see what we can do. First of all, I look at the numbers. I have a 2 here and a 3 here. I can say, what are the, what's 2 times 1, 2 times 2, 2 times 3, and so forth. And I can do that with the 3. 3 times 1, 3 times 2, and I look for a common number there. I see that if I multiply the first denominator by 3 and the second denominator by 2, I'm going to get a 6. I found the number. I need to go one step further, though, because I have a y squared in the first term and a y in the denominator of the second. What must I do there? What I've done here is notice that, first of all, I need to multiply the top by a 3, and that gives me 6y squared. I need to multiply the denominator of the second one by a 2 to get a 6. But what must I multiply a y by to get y squared? A y. Then if I've multiplied the denominator of the upper fraction by 3, I need to multiply the numerator by the same thing, and the same goes for the lower term. Completing this, I get 9 over 6y squared, and then in the second term I get 10y. 5 times 2y is 10 times y over 6y squared. I've multiplied the denominators of the two by what I need to get a common denominator, 6y squared. Now I can add those two together. Notice when I add them, I'm done. I can't go any further here because I don't know what y is. It could be 1, 2, 3. It's a variable. I'm not sure what it is. I can't combine it with the 9. I need to leave it in this form. Let's add these two, 2x over 3yz squared, and we're going to add that to y over 4z. First, we need to deal with getting a common denominator in terms of the numbers. I see that if I multiply 3 by 4, I get 12, and then I have 4z. If I multiply that by 3, I get 12. Now I need to reconcile the yz squared in the top number with the z in the bottom. What must I multiply that second denominator by to get a yz squared? I see that there's no y in the second denominator. I need to throw a y in. And in order to make z squared out of z, I need to throw in another z. Now I multiply the numerators by the same things. Notice that I have the same denominator in both cases, 12yz squared. Multiplying the numerators, I get 8x over 12yz squared for the first term, and 3y squared z over the 12yz squared for the second. Adding those together gives me that. That's as much as I can do, because 8x and 3y squared z contain totally different things. You cannot add them together, so you stop there. Let's look at a rule to add or subtract rational expressions. You basically follow method 2. You look for the least common denominator for the numbers. Then you figure out which variables you need to multiply any of the terms that you're trying to add to get a common denominator. You upscale the numerators. In other words, you multiply the numerators by whatever factor you had to multiply the denominators to keep the fraction the same. Then you do whatever the arithmetic operation is to go on. We'll look at some more examples. Here is 3 over 7ab cubed plus 2 over 3a squared b. We need to find what we need to multiply both of those by to get a common denominator. First of all, I see that I need to get a 3. What do I multiply 7 by? What can I multiply 3 by? I see that I need, in order to cover the a squared in the second denominator, I need to multiply the first one by an a. And then there's a b cubed up in that top term denominator. What must I multiply the b by in the second one? I must multiply that by b squared. Then I multiply the numerators by those same factors in this case, and I get 9a over 21a squared b cubed in the first, 14b squared, 2 times 7 is 14, in the second. Then I can add those two together. I get 9a plus 14b squared. Again, they're not like terms. I can't add them together. And I'm done here. Let's look at adding and subtracting mixed numbers now. Let's look at adding 7 1/8 to 3 5/6. There are a couple of different ways of doing this. The first way, which will always work, it's absolutely infallible, is to first change the mixed number to an improper fraction. Then we look for a least common denominator between 8 and 6. If I start thinking of multiples of 8 and multiples of 6, what's the first thing that might occur to me? If I multiply the top term, numerator and denominator, by 6, and the second one by 8, I'll have 48 in each case. Then I'll get 342 48ths and 184 48ths, two improper fractions. Now we can add the two of these together. When we do, we get 526 48ths. Maybe it would be worth simplifying here. I see that there's a common factor of 2. When I do that, I get 263 24ths, and now I can convert this back to a mixed number. When I do, I get 10 and 23 24ths. Notice in this case, I didn't go after a least common denominator. I just multiplied the two denominators together to get the fastest thing I could do, which was a common denominator. Let's work this same problem again, but look at it in terms of a least common denominator. Now I have a 1/8 and a 5/6, and I start to think about numbers that these might have in common that are less than 48. I remember that 8 times 3 is 24, and 6 times 4 is 24. That's probably the least common denominator. Let me multiply by that. Then I have those two fractions as 3 24ths and 20 24ths. Then I can add those. I have 7 and 3 24ths, 3 and 20 24ths. I don't have to change these things at all now to an improper fraction, because I look at them and I see that 7 plus 3 is 10, 3 24ths plus 20 24ths are 23 24ths, and again I get 10 and 23 24ths as the result, as the sum. But in this case, I didn't have to go through all of the math. And the point here, when you do these kinds of problems, there are many, many ways of doing it, and you can pick one way and it'll be harder or easier. But the point is that after you do a number of them, you'll be able to say, oh, well, maybe I should just do it this way because it's the most straightforward. It really doesn't matter which of the many ways you might choose to do a problem, as long as you follow it step by step and get the correct result. But if you practice a lot, you'll develop an intuition as to which of a lot of different methods will give you the result in the fastest way possible. Let's try another one here. 5 3/4 and 4 7/10. We look at those and ask, is there a least common denominator? And I think, what can I multiply 4 by and 10 by, other than 4 times 10 is 40? I know that'll work, but let's be clever. How about 20? 4 times 5 is 20, 10 times 2 is 20. Upscale those fractions, and the fractional parts of those mixed numbers become 15 and 14. Now I have to add 5 and 15 20ths and 4 and 14 20ths. I'll bet you can see what's coming now. When I add these two together, I get 9 and 29 20ths, itself an improper fraction. Let me rewrite the fractional part of that. I have 9 and 29 20ths. That can be written as 9 and 20 20ths plus another 9 20ths. What's 20 20ths? It's 1. 9 plus 1 is 10, and I'm left with the 9 20ths. This is another way of looking at adding mixed numbers, and when the fractional part is greater than 1, you can split the part greater than 1 out and add it back into the number part of the mixed number. How can we summarize this? When we're adding two mixed numbers together, we upscale the fractions so that they have identical denominators. Again, it's probably easiest to do the math if you can find a least common denominator, and if you're stuck, a common denominator will work. We change the numerator so that the value of the fraction remains the same. Then we add the numerators and keep the denominator from step 1. Or we can add the whole number parts. Then we can change the improper fraction to a mixed number, combine the whole numbers, and we're done. Now, subtraction works very much the same way. Let's subtract these two things. Again, this is very straightforward because we have 3 minus 1 is 2, 3/4 minus 1/4 is 2/4. On the face of it, subtracting two mixed numbers is almost like subtracting integers. However, let's look at this case. Now, if we subtract 3 minus 1, we get the same 2, but if we subtract 1/4, 3/4 from 1/4, we're going to wind up with a negative number. What we need to figure out is how to deal with a situation like this. Of course, one way is just to change them both to improper fractions and keep going, but let's play with this just to see what happens here. What we can do here is say that 3 is equal to 2 plus 1, duh, well, that's okay, we know that, plus 1/4, and then we have minus 1 1/4. But now what I'm going to do is use that 1 and make that 1/4, add that 1 to the 1/4, and make an improper fraction, but it will allow me to do the subtraction. Because what I have now is 2 plus 4/4 plus 1/4 minus 3 3/4. That gives me 2 5/4 minus 1 3/4. Now I can subtract the fractions. 5/4 minus 3/4 is 2/4. I get 1 2/4, or I see that I'm not quite done yet. That's equivalent to 1 1/2. And again, if I wanted to represent this as a diagram, there is 3 1/4 minus 1 3/4. Or I have the 13 parts is 3 1/4, 7 parts is 1 3/4. What is the 6 parts that are left when starting with 13, removing 7, we have 6 left. Therefore, I have 6/4, or 1 2/4, or 1 1/2. So if you think about these things diagrammatically, it may help you. Here's a rule. When we're subtracting mixed numbers, you may need to borrow from the minuend. That's a fancy word of the number you're subtracting from. Whole number, convert it to an equivalent fraction in order to proceed with the fraction. Then we convert the mixed numbers to improper fractions and proceed. Now here we have two negative numbers. How do we deal with those? Again, we can change them to improper fractions. Then we can look to see what we could use as a common denominator. And in this case, if I multiply the 3 by 8 and the 8 by 3, then I can proceed here, and I have minus 224ths minus 69/24 to give me a total of minus 269/24. Then, of course, I need to find this as a mixed number. When I do the division, I get that's equivalent to minus 11 5/24. Let's look at solving equations. For example, you might remember that when we need to subtract the same thing from both sides of an equation, and then we need to get w by itself. In this case, what you do to one side of an equation, you do to the other, and the idea is to get the unknown by itself. Here we have x plus 2 1/4 equals 5 3/5. What must I do? I subtract 2 1/4 from both sides of that equation. That gives me x is equal to something. It gives me 5 3/5 minus 2 1/4. I need to find a common denominator there. Then I need to proceed to actually do that subtraction. When I'm done, I see that x is equal to 3 7/20. In reality, this is just like solving any equation dealing with whole numbers, except now your additions and subtractions are going to involve fractions as well, and you just make use of everything we've learned up to this point in terms of adding and subtracting fractions and mixed numbers to solve these equations. We're going to look now at a particular application near and dear to my heart of fractions, and it might be an unusual one that you might not think about, but math, in particular, adding fractions with different denominators is very common in music. In musical notation, you have notes that are shaped differently and they indicate different things. A note with a stem, a dark note with a stem, is considered to be a 1/4 note. A note with a stem and a flag is an eighth note. It has half the value of a quarter note. When you see a dot after a note, it means add half again the number of beats as the note's worth. If I look, I see that the signature of this piece of music says that there are 3 beats to a measure, and each quarter note gets 1 beat. Let's add the fractions up in that measure. I see that I have a quarter note. Then I add half again the value because it's a dotted quarter note. That gives me another 1/8. Then there's an eighth note, and then there's another quarter note. Let's see what the total number of beats I have in that measure add up to. I have 1/4, which is 2/8, plus 1/8, plus another 8, plus another 2/8. And I see that in that measure, I have 6/8. In other words, that adds up to 3 beats where each quarter note gets 1 beat. If you add up the values, the time of each of the notes within a measure, they all add up to the same.